Thank you for attending this presentation. I am Andrew Norfleet, and today we'll be looking at the experimentally determined densities of deuterated solvents for use in NMR spectroscopy. We're going to begin by looking at nuclear magnetic resonance, or commonly referred to as NMR. So that's kind of the purpose of this work, is for applications there. NMR is a critical analytical technique, so you can use it either qualitatively or quantitatively in everything from synthesis work to unknown analysis to thermodynamic equilibria or even kinetics. So a strong magnetic field is applied to the sample, and that's going to separate the hydrogen nuclei into either a spin up or spin down configuration, so either aligned or opposed with a magnet. And then radio frequency light that's resonant with the difference in energy of these two populations, which are governed by the Boltzmann distribution, is going to probe the molecular environment, and based on how shielded or deshielded each of the nuclei are, they'll show up at a different frequency. Now, the field strength isn't going to be perfect, so we require a lock frequency in order to determine where the protons are actually showing up. And deuterium is present in the solvent, and that usually provides a lock for modern instrumentation. So deuterated solvents also have the benefit that they minimize the obstruction in the area of interest. So on the right here, you see a common NMR spectra. This was taken on a 500 megahertz instrument here at MSU, and this is actually caffeine. So around 7.25, what you're observing here is the software is picking up a peak when that is actually the deuterated chloroform, which is the solvent used here. Because the deuteration is not going to be perfect, you'll have a small amount of hydrogen in the sample, and that will show up in NMR. You can imagine that if there were no deuteration, you would have an extremely large signal compared to the analyte that would kind of drown out some of those characteristics that you're looking for. A key part of sample preparation with deuterated solvents is that in order to determine the true concentration, particularly at different temperatures, you have to know the density values. And that was something where we noticed there are very few, if any, literature values for density of deuterated solvents. So this work will seek to elucidate those values for 12 common laboratory solvents. When choosing a solvent, there are several factors to consider. So primarily you're going to be looking at the analyte solubility, so you need to make sure your analyte goes into solution, and the experimental temperature, so you don't want the solvent to boil off in the instrument. Additionally, you can consider the viscosity of the solvent and the stability of the instrument. Chloroform with one deuteron is going to be a lot easier to produce here. For reference, chloroform D is about 50 cents a gram. DMSO D6 is about $3.50 a gram. Compare that to the isotopologues without deuterium on them. Chloroform is going to be 45 cents a gram, and DMSO is 68 cents a gram. So significantly more expensive to put those 6 deuterons on DMSO. The DMA45 was married with a Thermo Fisher Scientific AC200 circulator that was able to do the entire experimental range from 5 to 95 Celsius. That coolant was circulated through about 18 inches of insulated tubing. All the samples were prepared with an inert nitrogen gas atmosphere in a glove box, then transferred to a slank line and degassed with freeze pump thaw method. The calibration was done with air and water at each temperature through the equations on the right. So the rho, or the density of the sample, is related to the period of oscillation tau squared minus constant b, all divided by a constant a. The a is determined between the period and the density of water and air, looking at the difference between those to give a slope. And then the b is a intercept value that uses the values of air. The air density values were taken from the Anton-Parr documentation through an equation, and the water values were taken from NIST fit values. Between temperatures, there was 12 minutes allowed and 5 minutes of equilibration to get to the experimental temperature. On the left, we have a plot of some of the density results that we got using this method. So on the bottom, we're seeing undeuteurated cyclohexane, with the upright triangle being our experimental data and the downwards triangle being literature values that were fit from NIST data that was accepted. So what we're seeing there is an excellent correlation between the two. the values are almost stacked on top of each other, which means that our calibration, our experimental procedure, were both sufficient. What we're also seeing in the circles here is the cyclohexane D12 is significantly higher than the undeuteurated, but it's hard to really make a meaningful comparison between these. A thread that is common to all of the solvents is that the deuterated solvents will have a higher density value at a given temperature, and then the maximum density can even occur at a different temperature with deuterated solvents versus their non-deuterated components. We can draw meaningful comparisons with the literature values for the deuterated solvents. So on the right-hand side here, we're seeing the same cyclohexane D12 plotted with all of the accepted deuterated density values. You can see that the temperature-dependent density compares well with most of the published sources, although the density of per-deuterose solvents is highly dependent on the percent deuteration. So this work had 99.6% deuteration in our solvent, whereas some of the literature values were as low as 97% deuteration or even not listed. So common reference methods do not consider percent D in the reporting of density values, making it critical to get a very high percent of deuteration. Another method for drawing comparisons is to look at the molar volumes of each species, which is defined as the mass density divided by the molecular weight to give moles per milliliter. What you're seeing for each species here is they're plotted in two different regions, but with the same axes units. And you can see that generally as temperature goes up, the molar volume will also go up, although there are some pretty significant differences between the different species to the extent that pyridine and THF-D8 actually are crossing over in the experimental range. To analyze the molar volumes, we'll plot both the isotopal logs on the same plot, as well as the delta VM. So delta VM is the difference in molar densities between the deuterated and non-deuterated solvents. That's the blue line shown here. And what that's indicative of is a different coefficient of volumetric expansion. Previous works in this field will sometimes estimate the mass density or the molar volumes from the room temperature values, which are often reported, and then extrapolate that to the temperature they are working at. What we're seeing here is that there isn't a constant difference in the molar volumes with temperature between the two isotopal logs, and this is something that actually needs to be done experimentally for determining these thermophysical properties. With the variance in the delta of the molar volumes, it's not possible to accurately predict the expected densities due to deuterium effects. So isotopes change the reduced mass, and that's going to be proportional to the bond strength. Essentially, deuterium is being held tighter to each of the molecules, which is giving it a smaller molar volume. Additionally, deuterium is known to form stronger hydrogen bonds, so this can be extended to the covalent bonds that we're seeing in the solvents. Looking at table 1, we can see that hydrogen and deuterium 0-point energy differences from Shaner and Kuma in 96. And we're seeing a significant difference here in their values for deuteration having the Table 1 here, taken from Shaner and Kuma, shows the differences in 0-point energies for hydrogen and deuterium on water. And what you notice is that when deuterium is present in the hydrogen bond, we're seeing a lower change in the 0-point energy compared to hydrogen. Again, extending this to covalent bonds, deuterium has a significant effect on how those bonds behave that isn't accurately predicted. In conclusion, we looked at the temperature-dependent density values for 11 solvents. Using this information, you can determine the exact concentrations for use in quantitative NMR work. Now, we showed that experimental values are necessary because it's not very easy to predict how the material is going to behave. And we actually looked at the effect of the deuterium that extends beyond molecular mass differences and actually changes the molar volumes of each species. Thank you very much for attending this presentation.